Hello there, and welcome to Life Beyond Seen, a quiet corner of the world where curiosity slows down, where questions are allowed to stretch out a little, and where the pace of thought can finally match the pace of breathing. This is a place for wandering ideas, for gentle science, and for those moments late in the day when the world feels loud but your mind is searching for something calm and steady to hold on to. Tonight, we're going to drift into one of the most remote and misunderstood places on Earth, not by travelling across land or sky, but by sinking slowly into water. Not the kind you swim in or sail across, but the kind that almost no one ever sees. The kind that sits quietly, far from human footsteps, far from cities, far from noise, holding secrets that have waited a very long time to be noticed. If you're listening from somewhere comfortable, maybe with the lights dimmed or the day finally behind you, take a moment to settle in. Perhaps you're lying down, or maybe you're just letting the hours soften around you. Wherever you are, whatever time it happens to be for you right now, you're welcome here. And if this gentle exploration ends up bringing you a bit of calm or curiosity, maybe even a sense of quiet wonder, then that's more than enough. A like or a subscription helps this little space continue, but there's no rush for any of that. For now, just listen. Because tonight we're talking about what hides in the most isolated water on Earth. Water covers most of the planet, yet so much of it remains unseen, unexplored, and deeply misunderstood. We often think of the ocean as something vast and open, but in reality, much of it is more secluded than the emptiest desert or the highest mountain peak. There are places beneath the surface that have not felt sunlight for millions of years, waters that have barely changed since before humans existed, pockets of isolation so complete that even bacteria have had to invent new ways to survive there. And unlike distant planets or deep space, these places are right here, quietly surrounding us, hidden in plain sight. It's easy to assume that isolation means emptiness. When people imagine remote water, they often picture endless blue nothingness, a blank expanse stretching in every direction. But water has a way of hiding complexity. What looks empty from above can be layered with motion, chemistry, temperature shifts, and life forms so strange that they barely resemble anything we recognise. Some of the most isolated waters on Earth are not just far away. They're cut off by pressure, darkness, chemistry, or time itself. And in those places, life behaves very differently. Think about the middle of the open ocean, thousands of kilometres from land, where currents move slowly and nutrients are scarce, or the bottom of a deep lake sealed beneath ice, untouched by air for centuries, or a pocket of water trapped beneath a glacier, isolated since before modern humans walked the planet. These are not just locations. They are environments with their own rules, their own rhythms, their own quiet histories, unfolding without observation. One of the strangest things about isolated water is how it challenges our idea of what life needs. We grow up learning that life requires sunlight, oxygen, warmth, and stability. But the deeper scientists look, the more those assumptions unravel. In some of the most cut-off waters on Earth, life thrives without light, without oxygen, and sometimes without even a stable temperature. Instead, it survives on chemical reactions, pressure, and timescales that make human lifespans seem almost non-existent. And yet, for all their remoteness, these waters are not entirely disconnected from us. They affect global climate, ocean circulation, and even the air we breathe. Some hold ancient records of Earth's past, preserved in layers of sediment and salt. Others may offer clues about how life could exist on other worlds, beneath the icy shells of moons or in oceans hidden far from stars. But before we go that far, it helps to slow down and look at what isolation really means in the context of water. Isolation is not just about distance, it's about separation. Separation from sunlight, from surface air, from regular mixing, from the familiar cycles of day and night. When water becomes isolated, it becomes its own world, chemistry changes, life adapts, time behaves differently. There are lakes on Earth that have no natural outlet, where water has been trapped for thousands of years. Over time, salts and minerals build up until the water becomes dense and inhospitable. Some of these lakes are so chemically extreme that a human could not survive more than moments in them, yet microorganisms flourish there, forming entire ecosystems invisible to the naked eye. These organisms don't rely on sunlight. They don't follow the same rules as surface life. They exist in a quiet balance shaped by pressure, chemistry, and slow change. Then there are the deep oceans, where isolation is not defined by distance from land, but by depth. As you descend, light fades, colours disappear, pressure mounts, sound travels differently. At a certain point, the ocean becomes a place where human senses lose their usefulness. And yet life continues. Strange, translucent creatures drift through the darkness. Fish with no eyes navigate by vibration and chemical trails. Some organisms live clustered around hydrothermal vents, feeding on minerals heated by Earth's interior rather than sunlight from above. These environments are not just remote, they are alien in the truest sense of the word. They operate under rules that feel foreign because they are so far removed from everyday human experience. And yet they are part of the same planet, governed by the same physics, connected through currents and chemistry to the water that falls as rain outside your window. What makes isolated water particularly fascinating is that it acts like a natural laboratory. Because these environments change so slowly, they preserve conditions that might otherwise vanish. In some deep-sea basins, water has been trapped for thousands of years, barely mixing with the rest of the ocean. In subglacial lakes beneath Antarctica, liquid water exists under kilometers of ice, sealed off from the atmosphere since before the last ice age. These places are not just remote, they are time capsules. Scientists who study them often describe the experience as more like archaeology than biology. Samples are extracted carefully, examined slowly, and treated with the same care you'd give to something ancient and fragile. Every molecule tells a story. Every microbe carries clues about survival under extremes. And sometimes, what's found there forces scientists to rethink what life even is. But isolation isn't only physical. Some waters are isolated chemically. They may be saturated with salt, stripped of oxygen, or filled with gases toxic to most life forms. In these places, the usual rules of biology break down. Organisms evolve to use sulfur instead of oxygen. Some produce energy in ways that seem almost impossible. Others remain dormant for decades, waiting for conditions to change by the slightest degree. And then there's the human relationship with these waters. For most of history, we didn't know they existed at all. We sailed over them, built cities near them, and assumed the depths were empty simply because we couldn't see into them. Even today, we've mapped more of the surface of Mars than we have of Earth's deep oceans. There are trenches deeper than any canyon on land, valleys and plateaus hidden beneath kilometers of water, unexplored not because they are unreachable, but because they're difficult, expensive, and unforgiving. Isolation, in water, is both a physical condition and a psychological one. It's why people feel uneasy looking into dark depths. It's why deep water triggers a sense of unease even in strong swimmers. The mind struggles with places it cannot fully imagine, and isolated water, by its very nature, resists imagination. It doesn't give up its details easily. It doesn't reveal its boundaries. It simply exists, patient and unmoved. What's remarkable is that despite all this remoteness, these waters are not static. They shift, slowly and subtly. Chemical gradients change. Microbial populations rise and fall. Tiny currents move nutrients over spans of centuries. In some cases, water that sank thousands of years ago is only now beginning to rise again, carrying with it traces of a past climate, a past atmosphere, a past version of Earth. And that raises a quiet, unsettling thought. Some of the water moving beneath the surface today may have last touched air when humans were just beginning to walk upright. Some of it may predate agriculture, cities, even language. It has been isolated for so long that its chemical signature holds memories older than civilization itself. As we continue, we'll move deeper into these places, into waters that rarely mix, rarely change, and rarely reveal themselves. We'll look at how life survives there, how scientists study it, and what these isolated worlds might tell us about life elsewhere in the universe. Not in a dramatic or alarming way, but in the slow, careful way that science often unfolds, one observation at a time. For now, just let the idea settle. Somewhere beneath the surface of this planet, far from sunlight and sound, water has been quietly existing for thousands or even millions of years, and within it things live, adapt, and persist, unnoticed, unbothered, and largely unknown. And as we ease further into this quiet exploration, it becomes clear that the most isolated waters on Earth are not empty at all. They are simply waiting to be understood. When people imagine emptiness, they often picture vast open spaces, a desert stretching to the horizon, a night sky with no stars, a silent room with the lights turned off. And when it comes to water, especially remote water, the imagination tends to do the same thing, an endless blue void. Flat, still, uneventful, a place where nothing happens because nothing can. But that idea, comforting in its simplicity, couldn't be further from the truth. Water has a strange way of disguising itself. On the surface, it can look uniform, even dull. From above, the open ocean appears like a single unbroken sheet, rippling gently, reflecting light, giving no hint of what lies beneath. Lakes look calm, motionless, almost inactive. Even satellite images, with all their sophistication, flatten water into a single colour, a blank patch between continents. And yet, beneath that apparent stillness, water is rarely empty. In fact, it may be one of the most densely layered, dynamic environments on the planet. The illusion of emptiness comes from our limitations as observers. Humans are creatures of light and air. Our eyes are tuned to the wavelengths of sunlight, our ears to vibrations carried by air. Water behaves differently. Light fades quickly as it moves through it. Sound bends, stretches, and travels in unexpected ways. Pressure increases dramatically with depth. What feels like a simple downward movement quickly becomes an entry into a world that doesn't operate on familiar terms. Even in the clearest ocean water, sunlight begins to vanish within the first few hundred meters. Reds disappear first, then oranges and yellows, until everything takes on a blue-grey tone. Go deeper still, and even blue fades away. Beyond that point, darkness becomes complete. Not nighttime darkness, not the kind your eyes can adjust to, but a thick, permanent absence of light. And yet, life continues there, unseen, often unnoticed, but very much present. What makes isolated water so deceptive is that its activity is rarely dramatic. There are no waves crashing, no winds howling, no visible movement from the surface. The processes that define these environments happen slowly, quietly, over long stretches of time. Chemical reactions unfold over decades. Microbial communities grow and shift over centuries. Currents move so gently they can take years to carry a particle a few meters. To a human observer, this looks like nothing is happening. But to the organisms living there, this is life as usual. Consider the deep open ocean, far from coastlines and surface productivity. Nutrients are scarce, light is gone, temperatures hover just above freezing, and yet countless organisms survive here, suspended in darkness. Some drift passively, conserving energy. Others move slowly, deliberately, adapted to a world where food is rare and effort must be carefully rationed. Many of these creatures are nearly invisible. Transparent bodies help them avoid predators. Some are so fragile that they disintegrate when brought to the surface. For centuries they remained unknown simply because our tools weren't delicate enough to capture them intact. It wasn't until deep-sea submersibles and advanced imaging came along that scientists realised how much life had been hiding in what was once thought to be empty space. Then there are the places where water becomes isolated not by depth, but by chemistry. Lakes with no outlet slowly accumulate salts and minerals. Over time, they become so dense that most organisms cannot survive in them. To the human eye, these lakes look barren, sometimes even lifeless. The water may appear oily, thick, or strangely coloured. But again, appearances deceive. In these chemically extreme waters, life doesn't disappear, it adapts. Microbes evolve mechanisms to survive intense salinity, acidity, or alkalinity. Some thrive in water that would burn human skin. Others metabolize compounds that would be toxic to most life forms. These organisms often grow slowly, dividing perhaps once every few days or weeks, but they persist, forming ecosystems invisible without a microscope. What's fascinating is how stable these environments can be. In lakes without inflow or outflow, the water layers often never mix. The top remains oxygenated, while the bottom becomes anoxic, devoid of oxygen entirely. The boundary between these layers can remain intact for thousands of years. On one side, life that breathes oxygen. On the other, life that finds oxygen deadly. Two worlds separated by a few meters of water, never touching. This kind of separation creates pockets of isolation so complete that evolution takes unusual paths. Organisms adapt not just to survive, but to exploit conditions that exclude almost everything else. They become specialists, finely tuned to their environment, often unable to survive anywhere else. In that sense, isolated water doesn't just hide life, it shapes it. There's also a psychological element to the illusion of emptiness. Humans tend to associate movement with activity. If something isn't visibly moving, we assume it's inactive. But water moves in ways that are difficult to perceive. Slow currents slip beneath faster ones. Temperature gradients cause gradual shifts. Dense water sinks while lighter water rises. These movements can be imperceptible moment to moment, yet over time they shape entire ecosystems. In the deep ocean, for example, there are currents that take centuries to complete a single circuit of the globe. Water that sinks near the poles slowly creeps along the ocean floor, eventually rising thousands of kilometers away. During that journey, it carries dissolved gases, nutrients, and chemical signatures from one part of the planet to another. It is motion on a timescale that dwarfs human experience, but it is motion nonetheless. Even in seemingly stagnant water, chemical reactions continue. Minerals dissolve, gases exchange. Microorganisms metabolize whatever energy sources they can find. Nothing is truly still. It only appears so because we are accustomed to faster rhythms. The illusion deepens when we consider sound. In air, sound fades quickly. In water, it can travel for enormous distances. Whales communicate across entire ocean basins. Ice cracking in polar regions can be detected thousands of kilometers away. The ocean is full of sound, much of it beyond human hearing, creating a constant acoustic landscape that we rarely notice. And yet, despite this constant activity, isolated waters often feel silent. That silence, too, is a matter of perception. Our ears are not built for underwater acoustics. What we interpret as quiet is simply sound moving in ways we can't sense. To the creatures living there, the environment may be anything but silent. There's also the matter of scale. Humans think in terms of meters, kilometers, minutes, and hours. But in isolated waters, meaningful changes happen over decades, centuries, or longer. A bacterial colony might take years to noticeably expand. A chemical gradient might shift imperceptibly over a lifetime. A deep water current might take longer than recorded human history to complete a cycle. When viewed on those timescales, stillness becomes a kind of illusion created by impatience. We look, don't see change, and assume none is happening. But the water does not operate on our schedule. This misunderstanding has led, historically, to dangerous assumptions. For a long time, the deep ocean was thought to be a dumping ground, a place where waste could disappear without consequence. After all, it looked empty. It seemed vast enough to absorb anything. But the reality is that isolated waters are often slow to recover. Pollutants can remain trapped for centuries. Disturbances can ripple outward in subtle ways, altering ecosystems that took millennia to stabilize. The same applies to deep lakes and enclosed seas. Because they exchange water so slowly, any disruption lingers. A change in temperature, chemistry, or nutrient input can take generations to correct itself. What looks resilient is often fragile, simply operating on a scale we don't intuitively grasp. There's a certain humility that comes from understanding this, the realization that emptiness is often fullness we don't yet understand, that silence is often sound beyond our range, that stillness is frequently motion slowed to a tempo we aren't built to notice. It also changes the way we think about exploration. When scientists first began studying isolated waters in earnest, they expected to find boundaries, limits, dead zones. Instead, they found continuity. Life extending farther, deeper, and into harsher conditions than anyone had predicted. Every time a boundary was drawn, something crossed it. This has profound implications beyond Earth. If life can thrive in dark, cold, chemically extreme water here, then similar environments elsewhere become potential habitats. Subsurface oceans on moons like Europa or Enceladus suddenly seem less far-fetched. The idea that life requires sunlight begins to crumble. Instead, energy, chemistry, and time become the central ingredients. But even without looking outward to space, there's something quietly remarkable about the way Earth hides its complexity. The most isolated waters are not hidden because they are unimportant. They are hidden because they operate beyond our usual frame of reference. They are slow, subtle, and patient. They do not announce themselves, they simply continue, and perhaps that's what makes them so compelling. In a world filled with noise, speed, and constant visibility, these places exist in near anonymity. They remind us that not everything meaningful needs to be seen. Not everything that matters makes a sound. Some of the most intricate systems on the planet operate in darkness, in silence, beneath layers of water and time. As we continue deeper into this exploration, we'll begin to look at the kinds of life that emerge in these environments, not the familiar fish and plants of coastal waters, but organisms shaped by pressure, darkness, and isolation. Life that challenges our definitions, blurs categories, and forces us to reconsider what it truly means to survive. For now, it's enough to sit with the idea that what looks empty rarely is, that beneath calm surfaces entire worlds can exist unnoticed, and that in the most isolated water on Earth, far from being voids, there are stories unfolding slowly, patiently, waiting for the moment when someone finally learns how to listen. There are places on Earth where the word empty begins to lose its meaning, not because nothing exists there, but because what exists is so sparse, so widely spaced, that it challenges our usual understanding of abundance and absence. These places are not deserts of sand or stone, they are deserts of water, vast stretches of blue that appear endless, uniform and still, yet conceal a quiet form of isolation unlike anything on land. The open ocean is often imagined as lively and full, teeming with fish and colour, but that image mostly belongs to coastlines and coral reefs, places where sunlight, nutrients and motion converge. Move away from those edges, far beyond the reach of rivers and continental shelves, and the ocean changes character. It becomes something else entirely, a blue desert, a liquid wilderness where life is rare, energy is scarce, and survival depends on extraordinary efficiency. These regions, known as oceanic gyres, occupy enormous portions of the planet. They are slow-moving, circular current systems that trap water in vast rotating patterns. The North Pacific gyre alone covers an area larger than many continents. From above, these waters look calm, almost serene. But beneath that surface lies one of the most nutrient-poor environments on Earth. In these places there is little mixing with deeper waters. Nutrients sink but do not return. Phytoplankton, the microscopic plants that form the base of the marine food web, struggle to grow. With fewer phytoplankton, there is less food for everything else. Life becomes sparse, widely spaced, stretched thin across a massive expanse of water. It's here that the phrase liquid loneliness begins to feel appropriate. Not because these waters are devoid of life, but because of how isolated everything within them becomes. Organisms may drift for weeks without encountering another living thing. Predators travel long distances between meals. Encounters are rare, brief, and often final. And yet, life persists. In these blue deserts, efficiency becomes the defining trait. Creatures evolve to conserve energy at every possible turn. Some become nearly transparent, reducing the need for pigment and making them harder to see. Others develop slow metabolisms capable of surviving on minimal nourishment. Movement is measured, waste is minimized, nothing is done without purpose. Even reproduction adapts to isolation. Some species release enormous numbers of eggs or larvae, trusting that a few will survive the vast emptiness. Others become hermaphroditic, able to reproduce with any encounter, no matter how rare. In such environments, opportunity cannot be wasted. The loneliness of these waters is not just biological, it is physical. Sound travels far, but little happens to make noise. Light fades quickly, and with it, visual reference points. A creature drifting here exists in a kind of perpetual nowhere, surrounded by water that looks the same in every direction. There are no landmarks, no shelter, no boundaries that can be easily sensed. For humans, this kind of environment is deeply unsettling. Sailors have written about it for centuries, long before science had names for currents or gyres. Accounts speak of endless days without sight of land, of seas so calm they seemed unreal, of a strange psychological weight that settled in when nothing changed for too long. The ocean, in these places, does not threaten with storms or waves, it overwhelms with sameness. And yet, this sameness is deceptive. Even in the most isolated parts of the open ocean, invisible processes are constantly at work. Microscopic organisms drift in slow spirals, feeding on traces of organic matter that fall from above. This material, sometimes called marine snow, consists of dead plankton, waste particles, and tiny fragments of life, sinking gradually through the water column. In the deep, it becomes one of the primary food sources, a faint but steady rain that sustains ecosystems far below the reach of sunlight. The rate at which this material falls is astonishingly slow. A single particle might take weeks or months to reach the deep sea floor, and yet over time it accumulates, providing just enough energy to keep life going. In this way, even the most isolated waters remain connected to the rest of the planet, though the connection is thin, stretched and delayed. Some of the loneliest waters on Earth are not even deep. Certain mid-ocean regions remain permanently stratified, with warm surface layers sitting atop colder, denser water below. These layers rarely mix. Oxygen from the surface cannot easily reach the depths. Nutrients from below cannot rise. The result is a biological standstill, a kind of ecological pause that can last for centuries. In these zones, life adapts not by thriving, but by enduring. Growth is slow, reproduction is infrequent, but stability is high. These systems change so gradually that a single human lifetime barely registers as a moment. And then there are places even more isolated than the open ocean. Seas cut off from global circulation, basins sealed by geography or salinity, bodies of water that have been trapped for thousands of years, evolving independently of the world around them. The Mediterranean, for example, was once nearly cut off from the Atlantic, becoming a series of hypersaline basins. In that period, much of its water evaporated, leaving behind vast salt deposits. When the connection to the Atlantic reopened, water rushed back in with unimaginable force, refilling the basin in what may have been one of the largest floods in Earth's history. But traces of that isolation remain, recorded in sediments and chemistry. Other seas, like the Black Sea, are still partially cut off today. Deep below its surface lies an anoxic layer, where oxygen does not exist. In that zone, hydrogen sulfide dominates, creating an environment lethal to most life. And yet, microbial communities persist, adapted to conditions that would be deadly anywhere else. The boundary between oxygen-rich and oxygen-poor water remains sharply defined, a stable line separating two very different worlds. These layers rarely mix. The deeper water remains trapped, sometimes for millennia, slowly accumulating chemical signatures of everything that has ever sunk into it. It is water that has not breathed fresh air since before recorded history. Water that holds a memory of past climates, past ecosystems, past ages of the Earth. This is the strange paradox of isolated water. It feels empty, but it is full of information. It feels still, but it carries motion on timescales we struggle to comprehend. It feels lonely, but it is interconnected in ways that defy easy mapping. Even more striking is how life responds to this isolation not with abundance, but with specialization. In blue deserts, there is no room for excess, no space for waste. Everything that exists does so because it has found a way to fit into a narrow window of possibility. These organisms are not generalists. They are specialists in survival under constraint. And that perhaps is why these environments feel so different from the rest of the world. They are not chaotic. They are not lush. They are quiet, efficient, and patient. They operate under rules that favour persistence over growth, endurance over speed. There is something almost meditative about that idea, a reminder that life does not always rush forward. Sometimes it waits, sometimes it drifts, sometimes it simply continues, unchanged, in the same place for longer than any human story. As we move deeper into this exploration, it becomes clear that isolation is not the absence of life, but a reshaping of it. The farther water is from sunlight, nutrients and motion, the more it demands from whatever dares to live within it. And those that succeed do so not through strength or speed, but through balance. In the next stretch of this journey, we'll begin to look more closely at the kinds of beings that inhabit these lonely waters. Not the familiar creatures of shallow seas, but the ones shaped by darkness, pressure and scarcity. Life forms that challenge our assumptions and quietly prove that even in the most isolated places on Earth, something is always finding a way to exist. From above, the surface of water often looks calm, even lifeless. A lake can appear perfectly still, reflecting clouds and sky as though it were a polished mirror. The open ocean, on a quiet day, can stretch out in every direction with barely a ripple, giving the impression of emptiness, of nothing happening at all. But this sense of stillness is one of the great illusions of the natural world. Beneath that tranquil surface lies a realm in constant motion, shaped by forces that operate slowly, quietly, and relentlessly. To understand what really exists beneath still water, it helps to set aside the way humans usually think about movement. We're used to speed, wind in trees, waves crashing, cars passing by. But underwater, especially in isolated environments, movement often happens at a pace so slow it feels almost suspended. Currents creep instead of rush. Temperatures shift by fractions of a degree over years. Chemical reactions unfold with patient inevitability. Life adapts to this rhythm, syncing itself not to hours or days, but to seasons, decades, sometimes even centuries. One of the first surprises waiting beneath the surface is that stillness rarely means stagnation. Even in water that appears unmoving, there are layers. These layers form based on temperature, salinity, and density. creating invisible boundaries that separate one part of the water column from another. Warm water floats above cold, fresh water sits atop saltier layers, oxygen-rich zones rest above oxygen-poor ones, and these layers can remain separated for astonishingly long periods of time. In some lakes and seas, this layering becomes so stable that the water at the bottom never mixes with the water above it. The lower layers grow darker, colder, and increasingly cut off from the atmosphere. Oxygen disappears, chemical conditions change, and slowly a completely different world emerges, one that most surface-dwelling organisms could never survive in. Yet life finds a way. Beneath the still surface, microorganisms begin to dominate. These are not the familiar bacteria that thrive in soil or freshwater streams. These are specialists, adapted to low-energy environments where every reaction must count. Some metabolize sulfur instead of oxygen. Others extract energy from iron, methane, or hydrogen compounds. They form thin, often invisible layers that cling to particles, rocks, or even to each other, building ecosystems measured in microns rather than meters. What's remarkable is how organized these systems can be. Even in complete darkness, without plants or photosynthesis, energy flows, matter cycles, waste becomes food. One species' byproduct becomes another's survival tool. It's a closed-loop system, quiet and efficient, sustained by chemistry rather than sunlight. In the deep ocean, this process reaches an extreme. Thousands of meters below the surface, pressure becomes immense. Temperatures hover near freezing. Sunlight is entirely absent. And yet, in these conditions, entire communities exist around hydrothermal vents. Cracks in the Earth's crust where superheated water pours out, rich in minerals. These vents create oases of life in an otherwise barren seascape. Bacteria thrive by converting chemicals from the vent fluids into energy, a process known as chemosynthesis. Larger organisms like tube worms, clams, and crustaceans depend on these bacteria, often housing them inside their own bodies. It's a system that bypasses sunlight entirely, powered instead by the heat of the planet itself. The existence of these ecosystems fundamentally changed how scientists think about life. Before their discovery, it was assumed that all life ultimately depended on the sun. The deep-sea vents proved otherwise. Life could exist in isolation from the surface, sustained by the Earth's internal energy, quietly persisting in darkness for millions of years. But not all hidden activity comes from extreme environments. Even in relatively shallow waters, beneath a calm surface, complex dynamics are at play. Temperature gradients cause slow convection. Dissolved gases move in subtle patterns. Tiny organisms migrate vertically over the course of a day, rising at night to feed and sinking again by dawn to avoid predators. This daily movement, known as Diel vertical migration, is the largest mass migration on Earth, happening every single day without fanfare or notice. Billions of organisms participate in this vertical dance, moving hundreds of meters up and down through the water column. From space, it would be invisible. From the surface, imperceptible. But in terms of biomass, it dwarfs anything happening on land. It is a silent rhythm, repeated endlessly, shaping food webs and nutrient cycles on a planetary scale. Beneath still water, time also behaves differently. Sediment settles slowly, layer by layer, recording environmental changes like pages in a book. A sudden volcanic eruption might leave a thin ash layer. A shift in climate might change the type of plankton that sinks. Over thousands of years, these layers build a detailed archive of Earth's history, preserved beneath the surface, waiting to be read. In isolated waters, this record remains especially intact. Without strong currents or frequent disturbances, sediments accumulate undisturbed. Scientists drill into these layers to reconstruct past climates, ancient ecosystems, even the history of atmospheric composition. In some places, the water above has remained so stable that the sediment record stretches back millions of years without interruption. This stability also allows unusual chemical environments to persist. In certain deep basins, hydrogen sulfide accumulates, creating conditions toxic to most life. In others, methane becomes trapped, forming icy structures known as clathrates. These substances remain stable only under specific combinations of pressure and temperature, making them fragile in the face of change. Disturb them, and the system can shift rapidly, releasing gases or altering ecosystems that have remained unchanged for ages. What's striking is how little of this complexity is visible from above. A ship can pass over a deep basin without any indication of the strange chemistry unfolding beneath its hull. A lake can look pristine and still, even as its lower layers harbour conditions unlike anything at the surface. The water hides its stories well. There is also an emotional aspect to this hidden world. Humans have a complicated relationship with water we cannot see into. Clear, shallow water feels inviting. Dark, deep water often feels unsettling. This reaction is ancient, rooted in survival instincts. Our ancestors learned to fear what they couldn't see, and deep water offers no visual reassurance. But that fear also feeds curiosity. The idea that something might be happening beneath the surface, unseen and unknown, has fueled exploration for centuries. From early diving bells to modern submersibles, humans have repeatedly pushed into these depths, not because they expected danger, but because the silence itself seemed to promise discovery. And each time we look more closely, we find that stillness is never truly still. Even in places where water appears motionless for years, molecular movement continues. Heat flows, gases diffuse, life adapts. Nothing remains frozen in time, even if change occurs so slowly that it escapes casual observation. The water may seem quiet, but it is never inactive. This realization shifts how we think about isolation. It's easy to assume that being cut off means being inactive or unimportant. But in nature, isolation often leads to specialization, stability, and resilience. Systems evolve to function efficiently within narrow constraints. They become self-sustaining, internally balanced, and remarkably persistent. As we descend further into this topic, the focus begins to shift from environments to inhabitants. The creatures that live beneath still surfaces are not merely surviving. They are finely tuned to their surroundings. Their bodies, behaviours and life cycles reflect the conditions of darkness, pressure and scarcity in which they exist. Some of them have no eyes. Others produce their own light. Some have metabolisms so slow they might go years between meals. Some may live for centuries. They are not built for speed or competition, but for endurance. And that endurance tells a story. It tells us that life does not need abundance to flourish. It does not need constant change or stimulation. Sometimes, all it needs is stability, time, and a narrow window of possibility. As we continue deeper, we'll begin to meet these inhabitants more closely. The ones that thrive where movement is minimal, light is absent, and isolation defines every moment of existence. The ones that reveal, more than anything else, just how adaptable life can be when the world grows quiet. There are moments in science when discovery doesn't feel like progress so much as contradiction. Moments when what's found seems to go against everything we thought we understood. The creatures that live in the most isolated waters of Earth belong squarely in that category. They're organisms that by all reasonable logic should not exist. And yet they do. Quietly, persistently, often invisibly. To understand why they seem so impossible, it helps to remember what life, as we usually define it, depends on. Light, oxygen, moderate temperatures, a steady supply of nutrients, a stable environment. These are the conditions under which most plants and animals thrive. They are the rules written into biology textbooks, the assumptions that shape how we think about ecosystems. And then there are the places where none of those rules apply. Deep beneath the surface, far from sunlight and often starved of oxygen, life continues under conditions that would kill almost anything we recognise. Pressure that would crush bone, temperatures that hover near freezing or soar beyond boiling, chemical compositions that resemble industrial waste more than anything natural. And yet, within these environments, organisms not only survive, they form entire communities. These are not creatures of speed or strength. They are creatures of endurance, of chemistry, of patience. One of the most striking examples comes from hydrothermal vent systems deep in the ocean. These vents form where tectonic plates pull apart or collide, allowing seawater to seep into the Earth's crust. There, it's heated by magma, infused with minerals, and expelled back into the ocean at temperatures that can exceed 400 degrees Celsius. To a human, this environment would be instantly lethal. The pressure alone would be crushing, the temperature scalding, the chemicals toxic. And yet, clustered around these vents are dense ecosystems unlike anything else on Earth. At the base of these ecosystems are bacteria that don't rely on sunlight. Instead, they use chemosynthesis, converting chemicals like hydrogen sulfide into energy. This process is entirely independent of photosynthesis. No sun required, no light at all. These bacteria form the foundation for entire food webs. Giant tube worms, some reaching over 2 meters in length, house the bacteria inside their bodies. They have no mouths or digestive systems. Instead, they provide the bacteria with chemicals from the vent water, and in return receive nutrients. It's a partnership so complete that neither organism could survive without the other. Nearby, clams, shrimp and crabs thrive in the heat and darkness, their bodies adapted to withstand toxins that would kill surface-dwelling species instantly. Some shrimp have lost their eyes entirely, replacing vision with heat-sensitive organs that help them navigate the scalding vent plumes. Others glow faintly, producing light through chemical reactions in their bodies. The first time scientists encountered these communities in the late 1970s, it rewrote biology textbooks overnight. Until then, it was believed that all life on Earth ultimately depended on sunlight. These creatures prove that life could exist in total darkness, powered by the inner energy of the planet itself, and hydrothermal vents are only the beginning. In the deepest parts of the ocean, known as hadal zones, pressure reaches levels that seem utterly incompatible with life. At the bottom of the Mariana Trench, for example, the pressure is more than 1,000 times greater than at sea level. It's enough to collapse steel structures, to distort solid objects, to crush anything not perfectly adapted. Yet even here, life persists. Tiny amphipods scuttle along the seafloor. Microbes inhabit the sediment. Fish with translucent bodies and gelatinous tissues drift slowly through the darkness. Their cells are structured differently, their proteins adapted to function under immense pressure. In some cases, the membranes of their cells are composed of unusual lipids that remain flexible, where ordinary membranes would fail. These creatures live in near total darkness, in water only a few degrees above freezing, under crushing weight. They move slowly, conserve energy, and feed on whatever organic matter drifts down from above. A dead fish, a fragment of algae, a whale fall which can sustain an entire community for decades. And then there are the organisms found in isolated lakes, sealed beneath ice or trapped by geography. Some of these lakes have remained untouched for hundreds of thousands, even millions of years. Take subglacial lakes beneath Antarctica. Buried beneath kilometers of ice, these bodies of water have been cut off from the surface since before humans existed. They are dark, cold, and pressurized. Yet when scientists began drilling into them with sterile equipment, they found signs of microbial life. These microbes survive without sunlight, without fresh nutrients, without seasonal change. They rely on chemical reactions between water and rock, drawing energy from trace elements released by slow geological processes. Their metabolism is astonishingly slow. Some may divide only once every few years or even decades. In human terms, this would be a kind of suspended existence. But for these organisms, it's normal. Time moves differently when energy is scarce. Then there are hypersaline lakes, where salt concentrations are so high that most life instantly dehydrates and dies. The Dead Sea is one such place, though it's not truly dead. Specialized microorganisms known as halophiles thrive there. Their cells are adapted to function in environments that would tear ordinary cells apart. These microbes use unique proteins and internal chemistry to balance the salt concentrations around them. Some even require salt to survive, dying if placed in fresh water. Their entire biology is inverted compared to most living things. In acidic lakes, where the pH rivals that of battery acid, life again finds a way. Acid-loving organisms metabolize sulfur and iron, leaving behind vivid colors in the water, reds, oranges, greens that seem almost artificial. These lakes often form in volcanic regions or mining sites, and to human eyes they look toxic and lifeless. But under the surface, microbial communities flourish. What unites all these creatures is not their appearance or behavior, but their relationship with energy. In the absence of sunlight and abundant food, they have evolved to use whatever is available, however inefficiently. They operate on the edge of what biology allows, extracting meaning from chemistry in ways that feel almost alien. And this is where the idea of shouldn't exist begins to unravel. Because these organisms don't break the rules of life, they expand them. They show that life is not defined by comfort or abundance, but by adaptability. That it doesn't require warmth, light, or even oxygen. Only a gradient. Some difference in energy that can be exploited. A chemical imbalance, a slow leak of heat from the Earth's interior, a trace of methane, a hint of iron. If energy exists, life may find a way to use it. This realization has had profound consequences beyond Earth. When scientists look at icy moons like Europa or Enceladus, they see oceans beneath frozen crusts, dark, pressurized, isolated oceans, possibly heated by tidal forces or geothermal activity. Once, these places were dismissed as lifeless. Now, they're among the most promising candidates in the search for extraterrestrial life. Not because they resemble Earth's surface, but because they resemble Earth's most extreme and isolated waters. And yet, for all their strangeness, these creatures are not monsters or anomalies. They are simply life, doing what life does when given time and the smallest opportunity. They grow, they adapt, they persist. There is something quietly humbling about that. It suggests that life is not a fragile accident, clinging desperately to ideal conditions, but a robust phenomenon that emerges wherever it can. That the boundaries we imagine are more about our own limitations than nature's. It also reframes how we think about isolation. These creatures live in places cut off from sunlight, from seasons, from the surface world. And yet they are not lonely in the way humans think of loneliness. They exist within networks, however small. They interact, they exchange energy. They belong to systems that have endured for ages. Isolation in their world is not emptiness. It is stability. As we move forward, this idea becomes even more striking, because the deeper we go, the more we find that isolation does not lead to absence, but to transformation. The creatures that shouldn't exist are not exceptions. They are examples of how life reshapes itself when the world removes everything familiar. And in the next stretch of this journey, we'll look at how pressure, darkness, and time combine to sculpt these beings into forms that seem almost unreal. Not as curiosities, but as living proof that even in the most unreachable waters on Earth, life does not merely survive. It adapts, quietly, patiently, and without needing to be seen. There is a point beneath the surface where sound changes its meaning. Not because it disappears, but because it behaves differently. It stretches, bends, travels farther than intuition expects. And eventually, as depth increases and light fades away completely, sound becomes one of the few remaining ways the world communicates with itself. This is where silence begins to feel heavy, not empty, but weighted with pressure. Pressure is one of the defining forces of deep water. It increases steadily with depth, quietly and relentlessly, adding another atmosphere every 10 meters. By the time you reach 1,000 meters below the surface, the weight pressing in from all sides is immense. At the deepest points of the ocean, pressure becomes almost unimaginable, strong enough to crush unprotected metal, collapse hollow structures, and distort materials that feel solid and immovable at the surface. For humans, pressure is something we experience only briefly, perhaps while diving or descending in an airplane. Our bodies are not designed to live under it. We are built for air, for moderate temperatures, for a narrow range of physical conditions. But in the isolated waters of the deep, pressure is not an occasional visitor. It is constant. It is the environment itself, and life there has adapted not just to endure it, but to depend on it. The pressure of deep water shapes everything. It alters the way molecules behave. It changes how proteins fold, how membranes hold together, how chemical reactions proceed. In high-pressure environments, even basic biological processes must be reimagined. Enzymes that work perfectly at the surface would malfunction or collapse entirely under such force. So deep-sea organisms have evolved versions of these molecules that remain stable, flexible and functional where ours would fail. This adaptation goes far beyond simple toughness. At great depths, even the concept of solidity changes. Bones become lighter, less rigid. Muscles grow softer. Bodies become more gelatinous, less defined. Many deep-sea creatures appear almost unfinished, translucent, fragile, as though they might dissolve if brought into the light, and in a sense they would. When removed from their native pressure, their structures can literally come apart. It's one of the reasons deep-sea exploration is so difficult. Bringing organisms to the surface often destroys them, not through injury but through decompression. The very environment that allows them to exist becomes lethal the moment it's removed. They are not built to survive without pressure. Pressure is their normal, and with that pressure comes silence of a particular kind. In shallow water, sound is chaotic. Waves crash. Marine animals vocalize. Human activity echoes through the water. But deeper down, the soundscape changes. High-frequency noise fades. What remains are low, resonant tones that travel for hundreds or even thousands of kilometers. The ocean becomes a place of long echoes and distant signals. In these depths, sound is not a constant clamour. It is sparse, deliberate. A distant whale call, the groan of shifting ice, the slow creak of tectonic movement. Sometimes mysterious noises that scientists still struggle to explain. The ocean hums, but it does so quietly, in frequencies more felt than heard. For the creatures that live there, this silence is not absence. It is information. Vibrations carry meaning. Pressure, waves signal movement. Danger, opportunity. Some animals have sensory organs designed specifically to detect these subtle cues. They feel the water rather than see it. They listen with their bodies, and yet despite all this activity, the deep remains profoundly still by human standards. There is no wind, no weather, no daily cycle of light and dark. Time stretches, moments blur together. Days have little meaning when nothing changes from one to the next. This stillness exerts its own kind of pressure. In isolated waters, especially those cut off from surface influence, change happens slowly, very slowly. A temperature shift of a fraction of a degree might take centuries. A chemical imbalance might persist for millennia. Life evolves at a pace that feels glacial, not because it is slow by necessity, but because stability allows it to be. In such environments, survival favours patience. Energy is precious. Movement is costly. Many deep-sea organisms barely move at all, drifting or anchoring themselves in place, waiting for nutrients to arrive. Some fish spend their entire lives within a small area, never travelling far, never encountering anything dramatically new. It's a kind of existence that runs counter to how humans usually think about life. We associate vitality with motion, growth, expansion. But here, vitality is measured in persistence, in the ability to endure unchanged for vast stretches of time, and that endurance creates a strange kind of silence. Not the silence of nothingness, but the silence of equilibrium. A system so finely balanced that disruption is rare. In some isolated basins, water has remained undisturbed for thousands of years. Layers do not mix. Oxygen never reaches the bottom. The chemistry remains stable across centuries. In these places, the silence is almost absolute, not because nothing exists, but because nothing disturbs the balance. When scientists sample such waters, they often find microbial communities that appear frozen in time. Their genetic makeup shows little variation. Their metabolic rates are incredibly low. Some are thought to survive on energy levels barely above the threshold of life itself. This challenges one of the core assumptions of biology, that life must be active to persist. In these depths, life survives by doing almost nothing at all, and yet it is precisely this stillness that allows it to endure. Pressure also shapes behaviour in more subtle ways. In high-pressure environments, sudden movement can be dangerous. A rapid change in depth can damage tissues. So animals evolve to move slowly, deliberately. Sudden bursts of speed are rare. Everything is measured, cautious, economical. Even predation looks different. There is no chasing, no dramatic pursuit. Instead, predators rely on patience, camouflage, or slow ambush. Some remain motionless for hours, sensing vibrations in the water, waiting for the faintest sign of prey. Others use bioluminescence, producing small points of light to lure victims close in the darkness. Bioluminescence itself is a response to pressure and isolation. In the absence of sunlight, light becomes a tool. It can attract mates, confuse predators, or signal warnings. In the deep, light is not something that comes from above. It is something life creates for itself, and yet, even this light is subdued. There are no blazing displays, no fireworks, just brief flashes, faint glows, subtle pulses that fade as quickly as they appear, enough to communicate, not enough to disturb the surrounding darkness. The deeper one goes, the more the world seems to slow down. Not in a literal sense, but in a perceptual one. Events are spread out. Reactions take longer. Life unfolds at a pace that feels almost suspended. This is where the pressure of silence becomes more than a physical phenomenon. It becomes psychological. For humans who descend into these depths, even briefly, the experience can be unsettling. Submersible pilots often describe a profound sense of isolation. The feeling of being completely cut off from the surface world. No light, no sound except the hum of machinery. No sense of direction. Just darkness pressing in from every side. It's not fear exactly. More like awareness. A recognition of how small, how temporary, how surface-bound we truly are. And yet, this environment is not hostile in the way we often imagine. It is indifferent. It does not resist intrusion. It simply exists, following its own rules, unmoved by presence or absence. That indifference is what makes it so powerful. In the pressure and silence of deep water, life has found ways to persist that seem almost philosophical. Not through dominance or speed or complexity, but through balance, through fitting perfectly into narrow ecological spaces, through accepting limitation rather than fighting it. There is a quiet lesson in that perhaps survival does not always require noise or movement, that sometimes endurance comes from stillness, from understanding the limits of one's environment and existing comfortably within them. As we continue this exploration, the focus begins to shift again, from pressure and silence to something even more profound: time. Because in these deep, isolated waters, time behaves differently. It stretches, it accumulates, It leaves traces that can remain untouched for longer than human history. And in those slow-moving layers, where pressure holds everything in place and silence reigns, the water begins to remember. That is where we will go next. There are places on Earth where time does not seem to move forward so much as it settles, where moments don't rush past but sink gently, layer by layer, into the quiet. These places are not loud or dramatic. They do not announce themselves. They simply remain, holding on to what has passed as though memory itself were something physical, something that could be stored in water and stone. Some of the most remarkable of these places are lakes. Not the lively lakes filled with boats and swimmers, not the ones that freeze and thaw with the seasons or change colour with the weather, but the rare, isolated lakes that exist almost outside of time. Lakes that have been cut off from rivers, from currents, from mixing. Lakes whose depths have remained undisturbed for thousands, sometimes millions of years. These are lakes that remember. At first glance, they often look unremarkable. A calm surface, no visible motion, maybe a faint ripple from wind or passing birds. But beneath that surface lies a history preserved with extraordinary clarity. Layer upon layer of sediment, each one a quiet record of the world as it once was. When scientists study these lakes, they do not just see water, they see time stacked vertically. Every year, particles settle to the bottom, dust carried by wind, pollen from distant forests, microscopic remains of algae and bacteria, ash from volcanic eruptions, even traces of human activity long after civilizations have risen and fallen. These particles accumulate slowly, forming thin bands called valves, each one marking a single year of deposition. In lakes that remain undisturbed, these layers are not churned or mixed. They remain in order, oldest at the bottom, newest at the top, and because the environment is stable, these layers can persist with astonishing clarity. Some lakes contain uninterrupted records stretching back tens of thousands of years. To scientists, these sediments are more than mud, they are archives. By analysing their chemical composition, researchers can reconstruct past climates, rainfall patterns, temperature shifts, even atmospheric conditions. A sudden spike in ash might reveal a long-forgotten volcanic eruption. A change in pollen types can indicate the arrival or disappearance of forests. Traces of heavy metals can mark the rise of industrial activity. All of this information lies quietly beneath the water, unchanging, waiting to be read. But the most fascinating lakes are those that go even further, those that have remained isolated not just from human disturbance, but from the world itself. Take Lake Baikal in Siberia, the deepest and one of the oldest freshwater lakes on Earth. It holds roughly 1/5 of the planet's unfrozen freshwater. Its depth exceeds 1,600 meters. Its age is estimated at over 25 million years. That age alone makes it extraordinary. Most lakes last only a few thousand years before filling with sediment or draining away. Baikal has endured through ice ages, tectonic shifts, and the rise and fall of species. It has done so because it sits in a rift valley, slowly deepening as the Earth's crust pulls apart. But what makes Baikal truly remarkable is not just its age, but its isolation. The deep waters of the lake are cold, oxygen-rich, and astonishingly clear. The lower layers mix very slowly, allowing ancient water to remain largely unchanged for centuries at a time. Within this isolated environment, life evolved in unique ways. Over half of Baikal's species exist nowhere else on Earth. There are sponges that filter the water to near transparency. Fish adapted to extreme cold and pressure. Tiny crustaceans that glow faintly in the dark. Entire ecosystems that have developed independently, shaped by isolation and time. Baikal is not alone in this. Across the world, there are lakes that have become biological time capsules. Lake Vostok, buried beneath nearly 4 kilometers of Antarctic ice, has been sealed off from the surface for at least 15 million years. The water beneath the ice remains liquid due to geothermal heat and pressure. For most of human history, no one even knew it existed. When scientists first realized there was a massive lake hidden beneath the ice, the implications were staggering. Here was a body of water that had been isolated since long before modern humans appeared. If life existed there, it would have evolved entirely independently of surface ecosystems. Drilling into such a lake is a delicate process. Any contamination from the surface could destroy its pristine conditions, so researchers proceed with extreme caution, using sterile equipment and slow methods. Even then, they tread carefully, aware that they are peering into a world that has not been touched for millions of years. Preliminary studies suggest microbial life does exist there. Organisms that survive without sunlight, without fresh nutrients, possibly relying on chemical energy from the surrounding rock. If confirmed, these microbes would represent one of the most extreme examples of isolation-adapted life on Earth. And perhaps more importantly, they would offer a glimpse into how life might exist on other worlds, beneath icy crusts and frozen surfaces. But not all memory-holding lakes are hidden beneath ice. Some are found in arid landscapes, where evaporation outpaces inflow, creating closed systems that trap everything that enters them. In these lakes, salinity increases over time, minerals accumulate, water becomes denser, heavier, layers form that do not mix, and at the bottom, conditions become hostile to most life. Yet even here, life persists. The sediments of such lakes often preserve an astonishingly detailed record of environmental change, a shift in rainfall, a prolonged drought, a period of warming or cooling. Even human activity leaves its mark, from ancient agriculture to modern pollution. Because these lakes do not flush themselves out, nothing truly disappears. Everything settles, everything is remembered. This makes them invaluable to science, but also incredibly fragile. Disturbing these systems can erase records that took tens of thousands of years to form. A single change in water chemistry can disrupt layers that have remained stable since before recorded history. And this is where the idea of memory becomes more than metaphor. Water, in these environments, does not forget easily. It holds on to chemical signatures. It preserves biological traces. It retains patterns long after the events that created them have passed. In a very real sense, these lakes are archives, storing information not in ink or stone, but in molecules and sediment. There is something quietly humbling about that. Human history feels long to us. Centuries feel immense. But these lakes have watched glaciers advance and retreat. They have recorded the rise and fall of ecosystems. They have persisted through shifts in climate that would reshape continents. And they have done so without awareness, without intention. Simply by being still, even the absence of movement becomes meaningful. In many of these lakes, the lack of mixing allows oxygen to disappear from the depths. In these anoxic zones, organic matter decays slowly, sometimes not at all. Ancient plant material, animal remains, even traces of microorganisms can remain intact for millennia. It's not uncommon for scientists to extract cores from lake beds and find organic material that looks almost fresh, despite being tens of thousands of years old. The cold, dark, oxygen-poor environment acts as a natural preservative. This preservation gives us an unusual gift, a chance to look backward, not through guesswork but through direct physical evidence, a chance to see how ecosystems responded to past warming events, how they recovered from disruptions, how resilient or fragile they truly were. And in an age where climate is changing rapidly, these records take on new significance. They offer perspective. They show that change is not new, but they also reveal how quickly systems can shift when thresholds are crossed. Yet for all their scientific value, there is something deeply poetic about these lakes as well. They are places where the past has not been erased, where time has not rushed ahead, where the world has left its fingerprints, gently pressed into layers of mud and water. Standing beside such a lake, it's easy to feel a strange sense of continuity. The air feels still, the water unmoving. The surface reflects the sky just as it did thousands of years ago. And beneath it all, the lake quietly holds its memories, indifferent to the passage of centuries. It reminds us that not everything is meant to move quickly, that some parts of the world exist to observe, not to change, to store, not to rush. And as we continue deeper into the story of isolated waters, this idea becomes more and more important. Because the farther we go, the more we realise that isolation is not emptiness, it is preservation. The lakes that remember are not frozen in time, they are carrying it. And in the next part of our journey, we'll begin to explore what happens when water becomes more than a record keeper. When it becomes a sealed world, locked away from the surface entirely, holding secrets that have not seen light in ages. That is where isolation becomes something else entirely. There comes a point where water stops behaving like a flowing substance and begins to act more like a vault, not sealed by walls or doors, but by conditions so stable and so unchanging that whatever enters is held in place, sometimes for tens of thousands of years. In these places, water does not merely carry history, it preserves it. When water becomes a time capsule, motion slows to almost nothing. Layers remain undisturbed. Chemistry settles into equilibrium. Temperature barely shifts. And what falls into these environments is not quickly recycled or erased, but quietly archived. Dust, pollen, microorganisms, chemical traces, even remnants of ancient life are locked in place, protected from the usual forces of decay. This happens most often in places where circulation is limited or non-existent. Deep basins, enclosed seas, subglacial lakes, isolated pockets of groundwater. Anywhere the normal rhythm of inflow and outflow is interrupted long enough, water begins to behave less like a river and more like a library. One of the clearest examples lies beneath ice. In polar regions, massive ice sheets press down on the land, sealing liquid water beneath them. The pressure and geothermal heat prevent the water from freezing completely, creating lakes hidden under kilometers of ice. These lakes are some of the most isolated environments on Earth. No sunlight, no contact with the atmosphere, no mixing with surface water, just darkness, cold, and time. Lake Vostok is perhaps the most famous of these hidden worlds. Buried beneath Antarctica, it remained unknown until the late 20th century. When scientists finally detected it using radar, they realised they were looking at a lake roughly the size of Lake Ontario, sealed off for millions of years. The implications were profound. Here was water that had been isolated since long before modern ecosystems developed. Any life within it would have evolved entirely on its own, shaped by conditions that no longer exist at the surface. Even the water itself was ancient, potentially unchanged since a time when the climate of Earth was very different. Drilling into such a lake is not a simple task. The risk of contamination is enormous. Introducing modern microbes into such a pristine environment would permanently alter it, destroying the very thing scientists hope to study. So research has been cautious, slow, and deliberate. When samples were finally analysed, signs of microbial life appeared. Not abundant, not diverse, but present. Life that had persisted in darkness and isolation for geological timescales. Life that had adapted to extreme cold, high pressure, and a complete absence of sunlight. What makes these environments extraordinary is not just their age, but their stability. On the surface of Earth, change is constant. Seasons shift, temperatures fluctuate, ecosystems rise and fall. But in these isolated waters, change happens so slowly that it barely registers. 1,000 years might alter nothing visible at all. That stability allows water to act as a memory keeper. Chemical signatures remain intact. Isotopic ratios reveal ancient temperatures. Dissolved gases record past atmospheric conditions. Even tiny variations in sediment composition can reveal volcanic eruptions, asteroid impacts, or shifts in global climate. In some cases, scientists can reconstruct year-by-year histories, stretching back tens of thousands of years, simply by reading the layers preserved beneath still water. It is like opening a book written not in words, but in molecules. But not all time capsules are hidden beneath ice. Some exist in the depths of oceans where water becomes trapped by topography and density. In these places, dense, salty water sinks and remains isolated from the layers above it. Because it is heavier, it does not mix easily. Over time, it becomes chemically distinct, aging slowly as it sits undisturbed. These deep water masses can persist for centuries or longer. The oxygen within them gradually diminishes. Organic matter accumulates. Chemical reactions proceed at a glacial pace, and yet nothing truly disappears. Even when oxygen is gone, life finds a way to persist. Microbes switch to alternative metabolic pathways, using sulfur, methane, or iron instead. These organisms operate on energy budgets so low that they challenge our definition of life itself. Some scientists believe certain microbes in these environments may divide only once every few hundred or thousand years. To us, that sounds almost like stasis, but to them, it is simply existence. What makes these environments especially compelling is how clearly they separate cause and effect. Because nothing is quickly flushed away, every change leaves a mark. A warming period increases biological activity, which alters chemical composition. A cooling period slows everything down. A shift in ocean circulation leaves a signature that remains detectable millennia later. Water, in these places, becomes a ledger. And it doesn't only record natural history, it records us. In many lakes and enclosed seas, scientists have found layers corresponding to human activity. Increased metal concentrations from early mining, soot particles from industrialization, synthetic compounds that could only have come from modern manufacturing. Even traces of radioactive fallout from nuclear testing have been preserved in sediments. These markers form a clear boundary between pre-industrial and modern times. A line in the mud that says, quite literally, this is when humans began to change the planet in measurable ways. What's striking is how quietly this record forms. There are no alarms, no announcements. The water simply accepts what enters it and holds on to it. Over time, it becomes impossible to deny the evidence. The past is there, layered beneath the present, waiting to be uncovered. In some isolated waters, the preservation goes even further. Organic material does not decompose fully. Ancient plant matter, pollen, and even soft tissues can remain recognizable after tens of thousands of years. This level of preservation is rare on land, where oxygen, bacteria, and weather quickly break things down. But in cold, dark, oxygen-poor water, decay slows dramatically. These conditions allow scientists to study ancient ecosystems with astonishing detail. What plants grew nearby, what the climate was like, what species thrived or disappeared. The water becomes a kind of biological archive, preserving snapshots of life long gone. And yet, there is something deeply humbling about this process. Because while humans strive to record history through writing, monuments, and digital storage, water does it effortlessly. It does not care what is important. It records everything indiscriminately. Dust, ash, pollen, pollution, life, death. All are treated the same. In this way, water becomes an impartial historian. It also becomes a reminder of how small our moment in time really is. Standing beside a lake that has existed for tens of thousands of years, it's impossible not to feel the scale of it. Generations pass, civilizations rise and fall, and the lake remains, quietly collecting evidence of each passing age. There is also a subtle tension in these time capsules, because while they preserve the past, they are also vulnerable to the present. A single disruption, a change in temperature, a shift in chemistry, a breach of isolation can alter them forever. Once mixed, they cannot be unmixed. Once contaminated, they cannot be restored to their original state. The memory is altered. This is why scientists approach these environments with such care, not just because they are scientifically valuable, but because they are irreplaceable. There is no second chance to study water that has been isolated for 1,000,000 years. Once disturbed, its unique history is gone. And yet, despite this fragility, these systems have endured for astonishing lengths of time. They have survived ice ages, tectonic shifts, and climatic upheavals. Their resilience comes not from strength, but from stability, from remaining unchanged while the world above transforms again and again. As we move deeper into the story of isolated waters, this theme becomes more pronounced. The idea that some of the most important processes on Earth happen slowly, quietly, without spectacle, that the deepest truths are often preserved in silence rather than noise. Water, in its most isolated form, does not rush. It waits, it holds, it remembers. And in the next part of this journey, we'll begin to explore what happens when isolation becomes so complete that even sound, light and motion nearly vanish altogether. Places where the boundary between life and non-life grows thin, and where the question is no longer what is preserved, but what can still exist at all. That is where the story begins to feel truly otherworldly. There is a kind of darkness that does not come from night. It is not the absence of the sun after a long day, nor the closing of eyes in a quiet room. It's a darkness that exists independently of time, one that remains even when the rest of the world is awake. This is the darkness that lives between the currents, in the deep places where water moves so slowly that motion itself feels like a rumour. To understand this darkness, it helps to understand how the ocean moves. From the surface, the sea appears dynamic. Winds push waves, storms churn water into chaos, tides rise and fall with clock-like precision. But beneath that restless skin lies another world entirely. A world governed not by weather, but by density, temperature and gravity. A world where motion is subtle, deliberate, and sometimes so slow that it takes centuries to complete a single cycle. These are the deep currents, not the familiar ones that carry ships across oceans, but the vast invisible rivers that flow along the ocean floor, driven by differences in temperature and salinity. Cold, dense water sinks near the poles and begins a long, quiet journey across the planet, creeping through abyssal plains and deep basins before eventually rising again, thousands of years later, in distant regions. Between these currents lie spaces of remarkable stillness, not truly motionless, but slow enough that change becomes almost imperceptible. These are the dark gaps between circulation where water lingers, isolated from the surface and shielded from disturbance. It is here, in these slow-moving voids, that some of the most unusual conditions on Earth take shape. Light never reaches these depths, not even a trace. The last photons are absorbed hundreds of meters above, leaving nothing but blackness. Temperature remains nearly constant, hovering just above freezing. Pressure is immense, and oxygen, so abundant near the surface, becomes scarce or disappears entirely. In such an environment, life does not behave the way we expect it to. Movement is minimal, growth is slow, energy is conserved with extreme efficiency. Many organisms exist in a state that seems almost paused, not because they are inactive, but because activity itself is expensive. Every motion must justify its cost, every reaction must serve a purpose, and yet, life persists. The dark between the currents is home to creatures that appear almost unreal. Fish with translucent skin and hollow bones, jelly-like organisms that seem more suggestion than substance, microbes that thrive in chemical gradients so faint they are nearly undetectable. Some of these organisms rely on what falls from above, a slow rain of organic debris, fragments of dead plankton, waste products, and the occasional larger carcass. This material drifts downward through the water column, decomposing as it goes until only the smallest remnants remain. By the time it reaches the depths, it is little more than a trace, but in the dark between the currents, even traces are enough. Other organisms draw energy from the earth itself. They live near fissures in the seabed, where heat and minerals seep upward. These are not the dramatic hydrothermal vents that host bustling communities, but quieter, colder seeps, releasing methane or hydrogen sulfide at a slow, steady rate. Around these seeps, life gathers, forming small islands of activity in an otherwise sparse landscape. What makes these places so strange is not just their isolation, but their consistency. Conditions change so little that evolution itself slows down. Species persist for millions of years with minimal alteration. Some organisms found in the deep ocean today resemble fossils from ancient geological eras, earning them the name living fossils. They are not relics in the sense of being outdated, but survivors of an environment that has changed very little since their ancestors first appeared. In this darkness, time feels different. At the surface, time is marked by cycles, day and night, seasons, storms, migration, growth and decay. In the deep, these cycles vanish. There is no sunrise or sunset, no seasonal variation, no sudden disruptions. The environment exists in a state of near permanence. This has a profound effect on life. Reproduction slows, lifespans lengthen. Some deep-sea organisms are believed to live for centuries. Certain species of coral, growing millimetre by millimetre, may be thousands of years old. Some fish show growth patterns suggesting lifespans far beyond what would be expected in shallower waters. The absence of light also changes how organisms perceive their world. Vision becomes less important. In its place, other senses sharpen. Sensitivity to pressure changes. Detection of chemical signals. Awareness of vibrations. The ocean becomes a place felt rather than seen. And in that sensory world, silence is not emptiness. It is information. A faint vibration might indicate the approach of prey. A subtle change in pressure might signal movement far away. A chemical trace might reveal the presence of food or danger. Everything is muted, but nothing is meaningless. For humans, this environment is deeply unsettling. When submersibles descend into these depths, the sensation is often described as otherworldly. There is no frame of reference, no horizon, no sound except the hum of machinery. The darkness feels absolute, pressing in from all sides. Yet even in that darkness, instruments detect life. The ocean floor, once thought barren, reveals itself as a landscape of slow activity. Trails left by creatures moving across sediment, burrows carved by invertebrates, bacterial mats forming delicate patterns across rocks. The signs are subtle but unmistakable. One of the most haunting aspects of these regions is how long they can remain unchanged. In some deep basins, water has not mixed with the surface for thousands of years. The chemistry remains stable, the temperature constant, the oxygen depleted long ago. These waters exist in a kind of suspended state, neither advancing nor retreating, and yet they are not dead. Microbial life continues to function, albeit at a pace so slow it challenges our understanding of metabolism. Some bacteria in these environments consume energy at rates barely above the minimum required to stay alive. They may divide only once every few centuries. Their entire existence unfolds on timescales that dwarf human civilization. This extreme slowness raises profound questions about what it means to be alive. If an organism barely changes over thousands of years, is it truly living in the way we understand life? Or is it something else? Something closer to a biological echo, sustained by chemistry rather than activity? The answer, it seems, is that life does not require speed or complexity. It requires continuity. A way to maintain structure, however slowly, against the pull of entropy. The dark between the currents provides just enough stability for that to happen. It also serves as a reminder of how much of the planet remains beyond our direct experience. The deep ocean covers more than half of Earth's surface, yet we have explored only a fraction of it. Vast regions remain uncharted, not because they are inaccessible, but because they are difficult to study, expensive to reach, and offer no immediate reward. And yet, These regions play a crucial role in the planet's systems. They store carbon, they regulate temperature, they influence ocean circulation, they act as buffers, absorbing change slowly and releasing it even more slowly. Without them, Earth's climate would be far less stable. There is also something quietly profound about the idea that so much of the planet exists in darkness, that life thrives not just in sunlight and abundance, but in absence and restraint, that some of the most enduring ecosystems on Earth are those that operate far from attention, far from noise. In the dark between the currents, there is no hurry, no competition for dominance, no rapid growth or collapse, just persistence. And perhaps that is why these places feel so alien to us. They reflect a version of existence that runs counter to human experience, a version where success is measured not by expansion, but by endurance, where survival means staying the same rather than changing. As we continue deeper into this journey, the theme becomes clearer. Isolation does not erase life, it reshapes it. Pressure does not destroy it, it refines it. Darkness does not end it, it teaches it to function differently. And in the next part of our exploration, we'll begin to listen more closely to the sounds that emerge from this darkness. The ones that travel vast distances through water, the ones we don't fully understand, the ones that hint at processes still unfolding far beyond the reach of light. Because even in the quietest places on Earth, something is always moving. And sometimes, if you listen carefully enough, the darkness speaks. There are sounds that belong to the world we know. Wind through trees, waves breaking on shore, the low hum of distant traffic. Even when we can't see what's making them, we understand them instinctively. Our minds trace them back to familiar causes, but deep beneath the surface of the ocean, there are sounds that do not behave this way. Sounds that arrive without warning, travel immense distances and fade without explanation. Sounds that resist easy classification, even after decades of study. These are not the cries of whales or the shifting of ice, though those too can be strange and haunting. These are signals that seem to emerge from the deep itself. Low-frequency pulses, metallic groans, rhythmic knocks, long, slow sweeps of sound that echo through thousands of kilometers of water before disappearing again. They are rare, unpredictable, and often recorded only once. The ocean is an extraordinary medium for sound. In water, sound travels faster and farther than it does in air. Certain layers of the ocean act like acoustic highways, channeling sound waves across entire basins with little loss of energy. A noise made in one part of the Pacific can be detected on the other side of the planet. This makes the ocean a place where even the quietest events can leave enormous acoustic footprints. And yet, despite this sensitivity, much of what is heard remains unexplained. Some of the most famous of these sounds were recorded by underwater listening stations during the Cold War. These systems were designed to detect submarines, but they picked up something else entirely. Strange signals with no clear source, no mechanical signature, no obvious natural explanation. One of the most well-known is a sound nicknamed the bloop. Detected in the late 1990s, it was an ultra-low frequency noise so powerful it was recorded by sensors thousands of kilometers apart. It rose rapidly in frequency, then vanished. At first, speculation ran wild. Some suggested massive undersea creatures. Others imagined geological events of unprecedented scale. Eventually, scientists determined that the sound most likely came from ice cracking or shifting in Antarctica, a process known as an ice quake. But even with that explanation, something lingered. The sheer power of the sound, the way it travelled, the fact that it emerged from one of the most remote and least understood regions on Earth. And the bloop was not alone. There were others. Upsweep, a rising tone recorded repeatedly over years with no clear pattern. Whistle, a sound that changed pitch like something alive. Slow down, a signal that decelerated in a way that defied easy interpretation. Each had possible explanations: tectonic movement, ice dynamics, oceanic currents interacting with seafloor structures, and yet none of them could be fully recreated or predicted. They appeared, were recorded, and then vanished back into the depths. What makes these sounds so unsettling is not that they're necessarily mysterious in origin, but that they emerge from places we cannot see and cannot easily access. They come from regions where pressure is extreme, light is absent, and human presence is minimal. They remind us that the ocean is not silent, even when it seems so. Sound in deep water behaves differently. It bends with temperature gradients. It travels farther in cold, dense layers. It reflects off seafloor ridges and underwater mountains. It can linger, echoing long after the source has stopped. In some cases, sound becomes the only reliable way to sense what is happening in the deep. Submersibles rely on sonar to map the terrain. Marine animals rely on sound to communicate, navigate, and hunt. In the absence of light, sound becomes the dominant sense. Whales, for example, use low-frequency calls that can travel across entire ocean basins. These calls pass through the same deep sound channels that carry unexplained noises. To a whale, the ocean is alive with echoes. To us, it is mostly silent, simply because we cannot hear what it is saying. But not all sounds are biological. Some originate from the slow shifting of the Earth itself. Tectonic plates grind past one another, releasing energy in the form of vibrations. Underwater landslides reshape the seabed. Methane hydrates destabilize and collapse. Each of these events produces sound, often in frequencies too low or too subtle for human hearing without instruments. And then there are sounds that seem to have no clear source at all. These are the ones that linger in scientific records, annotated with question marks. Signals that don't match known patterns, that don't repeat consistently, that appear in one place and never again. They're not loud enough to be alarming, but strange enough to remain unresolved. Part of the reason for this mystery is simply how little we monitor the deep ocean. Compared to land or atmosphere, our coverage is sparse, sensors are few, expeditions are rare. Many sounds are recorded by chance, picked up incidentally by instruments meant for other purposes. This leaves large gaps in understanding. A sound might be detected once, then never again, leaving scientists to speculate based on limited data. Was it a geological event? A biological one? Something else entirely? Without repeat observations, answers remain elusive, and yet the idea that the deep ocean produces sounds we don't yet understand is not particularly surprising. The environment itself is complex. High pressure alters physical properties, temperature gradients bend sound waves, chemical reactions release energy. Even water moving slowly through narrow spaces can produce unexpected acoustic effects. What is surprising is how these sounds affect us. Even when explained, they carry an emotional weight. There is something about hearing a noise from the deep, one without a visible source, that stirs unease. Perhaps it is because sound implies activity, presence, motion. And when that presence cannot be seen or identified, the imagination fills in the gaps. This reaction is ancient. Long before technology, humans listened for sounds in the dark to detect danger or opportunity. The ocean, vast and opaque, triggers that instinct more than almost any other environment. We cannot see what moves beneath us. We can only hear it, faintly, if at all. And so, when an unexplained sound is recorded from the deep, it resonates beyond science. It touches something more primal, a reminder that there are still parts of this planet that operate beyond our awareness. It's important to note that none of these sounds suggest anything supernatural. They do not imply unknown creatures or hidden forces. They are almost certainly natural phenomena, products of physics and geology and biology interacting in complex ways. But the fact that we cannot immediately explain them tells us something important. It tells us how limited our perspective still is. Despite satellites, sensors, and submersibles, the deep ocean remains one of the least understood environments on Earth. We have detailed maps of the moon's surface. We have walked on Mars remotely. And yet, vast portions of our own planet's depths remain unobserved. The sounds that emerge from these depths are like echoes from a place we have not yet fully explored. Clues, perhaps, to processes we don't yet comprehend. Or simply reminders that the Earth is still active, still changing, still full of movement even where we assume there is none. There is also something strangely comforting in that idea. In a world increasingly mapped, measured, and monitored, it is reassuring to know that some mysteries remain, that there are still places where nature operates on its own terms, unconcerned with observation or explanation. The deep ocean does not perform for us. It does not announce itself. It simply exists, producing sounds when conditions align, then returning to silence. And that silence too is meaningful, because between those rare sounds lies a vast stretch of quiet, a quiet that holds pressure, darkness, and time, a quiet that supports life in forms we are only beginning to understand, a quiet that reminds us how much of the world remains beyond our senses. As we continue forward, that quiet will take on a new dimension, because in the next part of this journey, we'll turn away from sound and towards something more personal, the way isolation affects perception, the way humans respond to environments that feel endless and empty. And in doing so, we'll begin to understand not just what hides in isolated water, but what it awakens within us when we think about it long enough. There is a particular kind of quiet that does not simply surround you, but settles into you. It is not the peaceful silence of a quiet room or a forest at dusk. It is deeper than that, heavier. The kind of quiet that comes from knowing there is nothing nearby, nothing moving, nothing responding. This is the quiet that defines isolation, and nowhere does it manifest more completely than in the most isolated waters on Earth. Isolation is not just a physical condition, it is a psychological one. And when humans encounter it, especially in environments as vast and indifferent as deep water, something subtle begins to change inside the mind. To understand this, it helps to consider how deeply social and sensory we are as a species. We evolve surrounded by cues, sounds of wind and animals, movement in peripheral vision, shifts in light and temperature, the presence of others. Even in solitude, our brains expect feedback from the environment, something to anchor us. Remove those cues, and the mind begins to behave differently. In isolated water environments, especially deep or enclosed ones, sensory input drops dramatically. Light disappears, sound becomes distant and distorted. Movement is minimal, the sense of direction fades. There are no familiar landmarks, no sky, no horizon. Just depth in every direction. For humans who have descended into these environments, whether in submersibles or diving chambers, the psychological effects can be immediate and profound. Time feels distorted. Minutes stretch, thoughts loop, awareness turns inward. Some describe a strange calm, others an uneasy tension they can't quite explain. It's not fear in the traditional sense. There is no immediate threat. Rather, it's the absence of stimulation that unsettles the mind. The brain, evolved to interpret constant input, begins to search for patterns. When it finds none, it sometimes invents them. This is one reason deep isolation has long been used as a psychological experiment, though rarely intentionally. Submariners, deep-sea researchers, and polar scientists often report similar experiences despite vastly different environments. A sense of detachment, altered perception of time, heightened awareness of one's own thoughts, a feeling that the world has narrowed to a very small, self-contained space. In underwater habitats, where crews may live for weeks or months, these effects become more pronounced. The absence of natural light disrupts circadian rhythms. Sleep patterns shift. Emotions flatten or intensify unpredictably. Even small irritations can feel amplified, while major concerns sometimes feel distant and unreal. This psychological response mirrors in some ways what happens in isolated natural waters themselves. Just as ecosystems adapt to low input and minimal change, the human mind adapts to isolation by conserving mental energy. Thoughts slow, attention narrows, awareness turns inward. Some people find this deeply uncomfortable, others find it strangely calming. There is a reason so many describe deep water as meditative, even hypnotic. The lack of external stimuli creates a kind of mental stillness. Without constant interruption, the mind drifts. Time loses its sharp edges. Thoughts become less linear, more fluid. In controlled environments, this can lead to introspection and creativity. In uncontrolled ones, it can lead to disorientation and anxiety. The difference often lies in preparation and context. When isolation is chosen, it can feel peaceful. When it is imposed, it can feel oppressive. What makes water unique in this regard is how completely it envelops you. On land, even in deserts or polar regions, the sky remains visible. There is always a sense of up and down, near and far. In deep water, those reference points vanish. Orientation becomes ambiguous. The body loses its usual cues. Divers often report that depth feels different from distance on land. Descending a few hundred meters can feel more profound than travelling thousands of kilometers horizontally. The pressure, darkness, and silence combine to create a sense of being removed not just from the surface, but from the familiar world entirely. This has a subtle psychological effect. The mind begins to feel small, not in a threatening way, but in a humbling one. The awareness of scale becomes unavoidable. The realization that there are places on Earth so vast, so deep, so indifferent, that human presence barely registers. For some, this sparks awe. For others, unease. There is a concept in psychology known as the overview effect, experienced by astronauts when they see Earth from space. It describes a shift in perspective, a sense of unity, and a re-evaluation of personal concerns. Interestingly, deep-sea explorers often report a similar effect, but inverted. Instead of seeing the planet from above, they experience it from within. Surrounded by darkness and pressure, they become acutely aware of how thin the layer of habitability really is, how narrow the band of conditions that allow human life to exist, and how much of the world operates beyond that band. This realization can be grounding, or it can be unsettling. There is also something about isolation that amplifies imagination. In the absence of visual detail, the mind fills in gaps. Sounds seem larger, shadows seem deeper, the unknown feels closer. This is why stories of the deep have always carried a sense of mystery, even fear. Not because of what is there, but because of what might be. And yet, prolonged exposure to isolated environments often produces the opposite reaction. After the initial discomfort fades, many people report a sense of calm unlike anything they've experienced before, a mental quiet that feels restorative, a slowing of internal noise. This mirrors what happens in nature itself. In isolated waters, systems tend toward equilibrium. Without constant disturbance, they stabilize. The same can happen in the mind. In the absence of distraction, thoughts settle, priorities rearrange, worries that once seemed urgent lose their urgency. The mind adapts to the stillness, just as organisms adapt to deep water. This is why isolation has long been sought intentionally, through retreats, monasteries, and solitary journeys. Humans have always known, intuitively, that stepping away from noise can reveal something deeper. Water, especially, seems to facilitate this process. Its rhythmic motion, even when imperceptible, has a grounding effect. There is also the matter of scale. In isolated waters, especially deep ones, scale becomes overwhelming. The distance to the surface, the weight of water above, the sheer volume of space. Confronting that scale can dissolve ego in a way few experiences can. This does not mean fear disappears. Rather, it transforms. Fear becomes curiosity. Tension becomes attentiveness. the mind stops resisting the environment and begins to observe it. This psychological shift is one reason deep-sea exploration is often described as transformative. Those who experience it rarely forget it, not because of danger, but because of the profound sense of perspective it provides. It forces a confrontation with limits, physical limits, sensory limits, conceptual limits. And in doing so, it highlights something important about isolation itself. Isolation is not inherently negative. It is context-dependent. In nature, isolation often leads to specialization, resilience, and stability. In the human mind, it can do the same when approached with care. The problem arises when isolation is unexpected, uncontrolled, or prolonged without support. Then it becomes disorienting, stressful, even harmful. Just as an ecosystem can collapse if cut off too abruptly, the mind can struggle if deprived of connection without preparation. But when isolation is gradual, intentional, and understood, it can become a space of clarity. This is perhaps why so many people feel drawn to water, especially vast, quiet bodies of it. Standing near the ocean, watching waves roll in endlessly, listening to their rhythm, can create a sense of peace that is hard to replicate elsewhere. It is not the water itself, but what it represents: continuity, scale, endurance. In the deepest waters, this effect is amplified. The world becomes simple. There is only pressure, darkness, and time. No distractions, no urgency, just existence. And in that simplicity, the mind often finds something it didn't realize it was missing. As we move forward, this psychological dimension becomes increasingly important, because the deeper we go into isolated waters, the more the environment begins to blur the line between physical and mental experience. The more it challenges our assumptions about what is necessary for life, for awareness, for meaning. In the next part of our journey, we'll look at how science grapples with this challenge, how researchers study environments that are difficult not only to reach, but to comprehend, and how the unknown continues to shape our understanding of what lies beneath the surface. Because in the end, the greatest mystery of isolated water may not be what lives there, it may be what it reveals about us. There is a moment in every scientific field when knowledge gives way to uncertainty, not because progress has stopped, but because it has reached the edge of what current tools and understanding can explain. In the study of Earth's most isolated waters, that edge arrives sooner than many expect. Despite satellites, deep-sea submersibles, autonomous drones, and decades of research, the vast majority of the deep ocean remains unexplored. Not just unmapped, but largely unobserved. We know more about the surface of the moon than we do about the deepest parts of our own seas, and the further down we go, the more questions begin to outnumber answers. One of the most persistent uncertainties lies in something deceptively simple: how life actually functions at the lowest possible energy levels. Scientists know that life requires energy. That much is clear. But how little energy is truly enough remains an open question. In isolated waters, especially those cut off from sunlight and fresh nutrients, organisms survive on amounts of energy that seem almost negligible. Some microbes metabolize so slowly that their activity barely registers. They may repair cellular damage only occasionally. They may reproduce once in a century, or even less. Their metabolism operates at the edge of what is physically possible. What science still does not fully understand is how these organisms maintain themselves for such long periods without degrading, how their cellular machinery avoids error, how proteins remain stable, how DNA avoids accumulating fatal mutations over such immense spans of time. There is a growing suspicion that we do not yet fully understand what it means to be alive at the most fundamental level, that life, rather than being a binary state, may exist on a spectrum, ranging from highly active to barely distinguishable from inert matter, and isolated waters are where this ambiguity becomes impossible to ignore. Another major unknown lies in how these environments evolve over geological timescales. We know that ocean circulation changes. We know that ice ages come and go. We know that continents shift and climates fluctuate. But we do not fully understand how isolated water bodies respond to these changes internally. Some seem remarkably resilient. Others appear to change suddenly, crossing thresholds that transform their chemistry and biology in ways that are difficult to reverse. What determines which path a system follows is still poorly understood. This uncertainty becomes especially important when scientists attempt to model future climate scenarios. Deep oceans and isolated basins act as massive reservoirs of heat and carbon. They absorb changes slowly and release them even more slowly. But exactly how much they can absorb, and for how long, remains unclear. There are feedback mechanisms at work that scientists are only beginning to identify. Methane hydrates trapped in deep sediments, for example, could release enormous amounts of greenhouse gas if destabilized. But under what conditions that might happen and how quickly is still debated. Similarly, the deep ocean's ability to absorb carbon dioxide is not infinite. There may be tipping points beyond which its buffering capacity weakens. If that happens, changes at the surface could accelerate in ways we are not prepared for. Then there is the question of biodiversity. We know that many deep-sea species have never been described. Some estimates suggest that the majority of marine life remains undocumented. But beyond that, we do not know how interconnected these organisms are. We do not know how the loss of one species might ripple through the system. In shallow ecosystems, food webs are relatively well understood. Remove one species, and the consequences can often be predicted. In the deep ocean, those connections are far more obscure. Energy flows are diffuse, relationships are subtle. Disturbances may take centuries to manifest. This makes studying impact extraordinarily difficult. When deep-sea mining, trawling, or drilling occurs, scientists cannot easily measure the consequences. The timescales involved are too long. The system's too slow to respond in ways we can observe within a human lifetime. In many cases, by the time damage becomes apparent, it may already be irreversible. Another major unknown concerns how isolated waters interact with one another. While we often think of deep basins as sealed systems, they are not entirely cut off. Slow currents, density shifts, and geological changes create connections that operate on timescales far beyond ordinary observation. Water that sank near the poles centuries ago may still be travelling along the ocean floor today. When it finally resurfaces, it carries with it chemical signatures from a different era. This slow circulation links distant parts of the planet in ways we're only beginning to map. But the details of these pathways remain elusive. Ocean models can approximate them, but small variations can lead to large uncertainties. A slight change in temperature or salinity can alter circulation patterns over vast distances. This makes prediction difficult. And prediction, in science, is often the true test of understanding. There are also mysteries that border on the philosophical. For instance, scientists still debate whether life in extreme isolation represents a fundamentally different form of biology or simply a variation on familiar themes. Do these organisms follow the same rules as surface life, just under different constraints? Or do they represent alternative strategies that challenge our definitions of life itself? The question becomes even more complicated when considering the possibility of life beyond Earth. If organisms can thrive in dark, pressurized, chemically extreme waters on our planet, then similar environments elsewhere become potential habitats. But how similar is similar enough? Would life in a subsurface ocean on a moon like Europa resemble Earth microbes? Or would it operate on principles we have yet to imagine? Without understanding the limits of life on Earth, it is difficult to predict what might exist elsewhere. There is also the matter of time. In isolated waters, time does not behave in ways that align with human intuition. Processes unfold over centuries. Evolution proceeds slowly. Chemical equilibria establish themselves over geological periods. When we attempt to study these systems, we are observing snapshots of much longer stories. This creates a fundamental challenge. We're trying to understand systems that operate on timescales far longer than our experiments, careers, or civilizations. We can measure them, sample them, model them, but we cannot easily watch them change. As a result, much of what we know about these environments is inferred rather than observed. We reconstruct histories from sediments, we extrapolate from chemical gradients, we build models based on limited data. These methods are powerful, but they are not complete. There are also technical limitations. Sending instruments into deep, isolated waters is expensive and risky. Equipment must withstand crushing pressure, extreme cold, and corrosive conditions. Communication is limited. Repairs are often impossible. Even when data is collected, interpreting it can be difficult. Signals overlap, variables interact. A single measurement can have multiple explanations, and sometimes data contradicts expectations entirely. There have been instances where instruments recorded chemical or biological activity that should not, according to current models, be possible. In some cases, these anomalies are eventually explained. In others, they remain unresolved, sitting quietly in scientific literature as open questions. What makes this uncertainty particularly striking is how little it diminishes with increased knowledge. Each discovery seems to open new layers of complexity. Each answer leads to deeper questions. This is not failure, it is the nature of exploration. The deeper we look, the more we realize how much remains hidden, not because it is deliberately concealed, but because it exists on scales and under conditions that do not align easily with human perception. And yet, this uncertainty is not a weakness of science, it is one of its strengths. Science does not require certainty to move forward. It thrives on doubt, on revision, on the willingness to admit what is not yet known. In the study of isolated waters, this humility is essential. There is also a quiet beauty in this not knowing. In a world where so much information is instantly accessible, where answers are expected immediately, the deep ocean stands as a reminder that some knowledge unfolds slowly, that some truths resist simplification. That understanding is sometimes less about arriving at conclusions and more about learning how to ask better questions. And perhaps that is why isolated waters continue to captivate scientists and non-scientists alike. They represent one of the last frontiers on Earth, not in the sense of conquest, but in the sense of curiosity. They invite patience, they demand respect, they challenge assumptions, they remind us that despite our technology, our maps and our models, there are still places on this planet that operate beyond our full comprehension. As we move forward in this exploration, this sense of uncertainty will become even more important, because in the next part of our journey, we will step away from what science can currently explain and look at the boundaries where knowledge fades into speculation, not in search of fantasy, but in recognition of a simple truth, that in the most isolated waters on Earth, some questions do not yet have answers, and perhaps for now, that is exactly as it should be. There is a moment that comes, usually after long enough exposure to silence, when the mind begins to do something curious. It starts to look outward, not for information, but for presence. Not in a dramatic or fearful way, but in a quiet, almost instinctive manner. A sense that if you are observing something long enough, perhaps it is observing you in return. This feeling is not unique to deep water, but the ocean has a way of amplifying it. Part of that comes from scale. When you're surrounded by water that stretches for kilometers in every direction, when light fades and sound softens, it becomes difficult to maintain the comforting illusion that you are the center of the scene. The environment feels older, larger, and more enduring than anything human. And in that context, awareness begins to shift. The question doesn't arrive suddenly. It drifts in slowly, like a thought you didn't realize you were having. Is anything down here aware of me? Not necessarily intelligent in a human sense, not watching with eyes or intention, but aware in the broader sense, sensing, responding, existing in a way that acknowledges presence. This is where the idea becomes unsettling, not because of danger, but because of uncertainty. In the deep ocean, many organisms perceive the world in ways we do not. They detect pressure changes, chemical gradients, electrical fields, and vibrations far too subtle for human senses. Some fish can sense the faint bioelectric signals produced by muscle movement. Others can detect minute changes in water displacement caused by distant motion. In such an environment, the concept of being unnoticed becomes complicated. A human descending in a submersible may feel invisible, wrapped in darkness and steel. But to organisms adapted to this world, that presence may be obvious. The low hum of machinery, the displacement of water, the warmth of a foreign object, the vibration of movement through an otherwise stable environment. To them, something has arrived, and that raises a quiet, uncomfortable thought. In places we consider empty or lifeless, we may simply be the least perceptive one as present. This is not to suggest intelligence in the way we define it. There is no evidence of thinking entities lurking in the depths, no hidden observers watching with curiosity or intent. But awareness does not require thought. It requires only sensitivity. And in the deep ocean, sensitivity is survival. Many deep-sea organisms respond instantly to changes in their environment. A sudden shift in pressure may cause them to retreat. A vibration may trigger bioluminescent flashes, either to confuse predators or warn others. Chemical signals ripple outward in invisible clouds, alerting nearby organisms to danger or opportunity. These responses are not conscious, but they are precise. They are tuned to a world where information travels differently, where light is absent and sound is slow and distorted. In such a world, the idea of watching loses its familiar meaning. There is no gaze, no focused attention. Instead, there is a constant low-level awareness of change, a sensitivity to disturbance, a readiness to respond. When humans enter these environments, we disrupt that equilibrium. Even the quietest submersible introduces noise, heat, motion. To us, it feels minimal. To a creature evolved for stillness, it may be overwhelming. And yet, the reaction is rarely aggression. More often, it is curiosity or avoidance. Creatures drift closer, illuminated briefly in the vehicle's lights, then fade back into darkness. Others remain motionless, relying on camouflage or stillness. A few may flee, their movements sudden and startling in the otherwise calm water. From the human perspective, this can feel like being observed, like eyes in the dark, even when none exist. The mind fills in gaps, evolution encourages caution. There is a psychological term for this, the sense of being watched in environments where sensory information is limited. It's a common experience in caves, deep forests, and open water. The brain, deprived of usual cues, becomes hyper-aware. It begins to search for patterns, for meaning, for agency. In deep water, this effect is amplified by the knowledge that you are not alone. Even if you cannot see them, you know life is present, that something is moving, reacting, responding. And because you cannot see it clearly, your imagination does the rest. This is why so many accounts of deep-sea exploration describe a strange tension. Not fear exactly, but a heightened awareness. A sense of being in someone else's domain. A recognition that the environment does not revolve around you. It is an ancient feeling, one that likely predates language. The awareness of entering territory that does not belong to you. In isolated waters, this feeling lingers because there is no visual confirmation to dispel it. No rustling leaves, no visible animals, just darkness and pressure, and the knowledge that life exists there in forms you do not fully understand. Science, of course, approaches this differently. It does not ask whether something is watching, but how organisms detect and respond to stimuli. And in that framework, the answer is clear. Many do. Deep-sea organisms are exquisitely sensitive to their environment. Some can detect a single molecule of a chemical drifting past. Others respond to minute vibrations transmitted through water or sediment. Some species of fish can sense electrical fields so faint they are barely measurable with instruments. From their perspective, the deep ocean is not silent or empty. It is full of information, constant, subtle, meaningful, and that raises an interesting inversion of perspective. Perhaps it is not that something is watching us. Perhaps it is that we are finally in a place where we are not the primary observers. This idea can be unsettling because it challenges a deeply ingrained assumption. Humans are used to being the ones who look, who study, who analyze. We place cameras, we take samples, we record data, we observe. But in the deep ocean, we become the anomaly, the disturbance, the fleeting presence in a world that existed long before us and will continue long after we leave. The creatures there do not need to understand us to respond to us. They simply react to change, as they always have. In that sense, our arrival is no different from a shifting current or a falling rock, another event in a long sequence of events. And yet, because we are conscious of ourselves, because we reflect on our own presence, the experience feels different to us. It feels personal. This is where the line between science and psychology blurs. The sensation of being watched is not evidence of observation. It is evidence of awareness, of the mind's attempt to situate itself in an unfamiliar environment, of the recognition that one is no longer at the top of the sensory hierarchy. In isolated water, the usual human advantages disappear. Vision becomes limited. Sound behaves strangely. Movement is slow and restricted. Technology becomes the only interface with the environment, and even then, it provides only partial information. This vulnerability can be deeply unsettling, but it can also be clarifying. It strips away the illusion of dominance and replaces it with something quieter: humility. Many deep-sea explorers have described a moment during their descent when this realization sets in. A moment when they stop thinking of the ocean as a place to be explored and start thinking of it as a place that simply exists, indifferent to their presence. In that moment, the idea of being watched loses its edge. It becomes less about fear and more about perspective. The understanding that life is not arranged around human perception, that awareness can take many forms, that observation does not require eyes or intent. It simply requires existence. There is something strangely comforting in this realization. The deep does not judge, it does not care, it does not react emotionally. It responds only to physical laws and biological imperatives. In a world so often shaped by human attention, by constant observation and reaction, the idea of a place that does not notice us at all can feel oddly peaceful. And yet, the question lingers, not because it needs an answer, but because it points to something deeper about our relationship with the unknown. We ask whether something is watching back not because we expect it to be, but because we are aware of our own act of watching. We become conscious of ourselves as observers, and in that awareness we recognize our smallness. In the end, the most honest answer is this: in the most isolated waters on Earth, there is no evidence of anything watching us in the way we watch the world. But there is constant interaction, constant response, constant awareness at levels we're only beginning to understand. The ocean does not look back. It does not need to. It simply continues, vast and patient, holding its secrets not in malice or mystery, but in depth, pressure, and time. And as we move forward, that understanding leads us to a final realization: that the greatest mystery of isolated waters is not what might be hidden there, but what these places reveal about the limits of our perception, our knowledge, and our place within the natural world. That is where the journey now turns. There comes a point, after moving through silence and pressure and distance, when the question quietly shifts. It stops being about what lives in isolated water and becomes something broader, something more reflective. What do these places, so distant from human experience, actually tell us about life itself? Not life as we imagine it, not the busy, visible, energetic kind that fills forests and cities, but life in its most fundamental form. Life stripped down to what is essential. Because when you look closely at the most isolated waters on Earth, what you find is not excess, not chaos, not abundance. You find restraint, efficiency, persistence, a kind of quiet discipline that feels almost deliberate, even though it is not. The first lesson these waters offer is that life does not need comfort. It does not require warmth, sunlight, or abundance. It requires only opportunity, a gradient, a difference in energy that can be used, however slowly, however subtly. In the depths, life learns to survive on margins so narrow they seem impossible. Where a human would starve, freeze, or suffocate, microbes continue to function. Where movement seems pointless, organisms evolve to barely move at all. Where time feels frozen, life stretches itself across centuries. This challenges one of our most basic assumptions, that life thrives best when conditions are ideal. In reality, life adapts to whatever conditions exist. Comfort is not a requirement. Stability is, and stability in isolated waters is abundant. There are no sudden changes, no rapid shifts, no seasons that force constant adjustment. Instead, there is consistency. Temperature remains steady. Chemistry changes slowly. Disturbance is rare. In such an environment, evolution favors patience over speed, conservation over expansion. This is why so many organisms in isolated waters appear unchanged over immense spans of time. They do not need to innovate rapidly. Their environment does not demand it. They survive not by outcompeting others, but by fitting precisely into a narrow ecological space and staying there. It's a form of success that looks very different from what we usually celebrate. Another lesson is that complexity is not always visible. On the surface, life often announces itself. Colours, movement, sound. In isolated waters, complexity hides. It exists at the microscopic level, in chemical pathways, in metabolic cycles that unfold over years instead of seconds. A handful of microbes in a deep-sealed lake may appear insignificant, but collectively they regulate chemistry, recycle nutrients, and maintain equilibrium. They form systems every bit as intricate as rainforests, just scaled differently in time and space. This forces a reconsideration of what richness means. Abundance of species is one form of richness. Stability of function is another. Isolated waters tend to favour the second. They also teach us that life does not require constant input. Many deep-sea ecosystems survive on what amounts to leftovers. Particles drifting down from above, chemical seepage from rock, energy that leaks slowly into the system rather than flooding it. This kind of existence would seem fragile, yet it often proves remarkably durable. Because it is not dependent on any single resource, it is less vulnerable to sudden loss. It adjusts, contracts, persists. There is a lesson here that extends beyond biology. In a world that often rewards speed, growth, and constant consumption, isolated waters demonstrate another way of being, one built on balance rather than expansion, on continuity rather than accumulation. They show that sustainability is not about having more, but about needing less. Another truth revealed by these environments is that life does not need to be visible to be significant. Some of the most important processes on Earth occur far below the surface, unnoticed by humans. Carbon cycling, nutrient transformation, chemical buffering. These processes shape the planet's climate and chemistry, yet they happen in silence. The deep ocean plays a crucial role in regulating Earth's temperature. It absorbs heat, stores carbon, moves energy around the globe on timescales that dwarf human history. Without it, the climate would be far more volatile, and yet, for most of human existence, we were unaware of these functions. The planet was regulating itself quietly, whether we understood it or not. This raises another subtle lesson. Understanding is not a prerequisite for existence. Life does not wait to be observed before it acts. It does not need recognition to continue. It operates according to physical laws, not human awareness. In that sense, isolated waters remind us that the world does not revolve around perception. They also challenge our sense of importance. When confronted with environments that have persisted for millions of years without human involvement, it becomes difficult to maintain the illusion that we are central to the story of life on Earth. We are participants, yes, influential ones, but not the authors of the system itself. There is humility in that realization. At the same time, there is connection, because despite the differences, life in isolated waters follows the same fundamental rules as life everywhere else. It uses energy. It maintains structure. It responds to change. It persists. The same principles that govern a microbe in a subglacial lake govern cells in the human body. The same chemical rules apply. The same balance between order and entropy exists. In this way, isolated waters are not alien. They are familiar in a deep, fundamental sense. They reflect life in its most reduced form, stripped of decoration and excess. They show us what remains when everything non-essential is removed. Another lesson emerges when we consider time. In isolated waters, time is not measured in days or years, but in geological spans. Change is slow. Effects accumulate gradually. Nothing happens quickly, but everything leaves a trace. This stands in sharp contrast to human systems, which often prioritize immediate results. We act quickly, sometimes without understanding long-term consequences. The deep ocean operates on the opposite principle. Actions echo forward slowly, sometimes imperceptibly, but persistently. It teaches patience, or perhaps it teaches caution. Because when changes do occur in these systems, they are often difficult or impossible to reverse. A chemical imbalance, a temperature shift, a disturbance in sediment can alter conditions for centuries. This is why scientists approach these environments with such care. They understand that even small interventions can have outsized consequences over time, and that brings us to one of the most important lessons isolated waters offer. That fragility and resilience often coexist. These ecosystems are resilient in that they can persist under extreme conditions, but they are fragile in that once disrupted, they may not recover within any meaningful human time frame. They remind us that durability does not equal invulnerability. There's also something quietly philosophical in the way life persists in isolation, without observers, without recognition, without purpose beyond continuation. It suggests that life does not require meaning to exist. Meaning is something we impose afterward. Life simply continues, adapting to whatever constraints it encounters, and yet in observing it, we inevitably reflect on ourselves. We see parallels between isolated ecosystems and isolated minds, between slow adaptation and personal resilience, between stability and stagnation, between survival and flourishing. The waters do not offer answers, but they offer perspective. They show that existence can be quiet, that progress does not have to be visible, that persistence can be its own form of success. And perhaps most importantly, they remind us that the world is larger, deeper, and more complex than our immediate experience suggests. That beyond the surface of things, beyond noise and motion, there are systems quietly holding the planet together. Systems that do not demand attention. Systems that endure. As we approach the end of this journey, the focus shifts one final time. Away from biology, away from psychology, away from speculation, toward reflection. Because after all we've seen, all we've considered, the most important question may not be what lives in the most isolated waters on Earth. It may be what those waters reveal about how we choose to live above them. There is a moment after spending enough time thinking about the deep when the mind begins to rise on its own. Not suddenly, not with urgency, but slowly, as if following a current it didn't realize it had entered. The weight of pressure eases, the darkness lightens, the silence becomes less absolute, and gradually, almost without noticing, attention drifts back toward the surface. This return is not abrupt. It doesn't feel like leaving something behind. It feels more like re-emerging after holding your breath for a long time, when the first inhale comes naturally and without effort. The world above feels louder, brighter, more active, but also strangely thinner, as though something essential was left behind in the depths. After spending time with isolated waters, it becomes difficult to see the surface in quite the same way. The ocean no longer feels like a boundary. A lake no longer feels shallow. Even a quiet pond carries a new sense of depth, not just physically, but conceptually. There is an awareness now that beneath what is visible, systems are unfolding slowly, patiently, independent of human attention. And this awareness lingers. One of the most striking things about returning from these thoughts is how quickly the world resumes its pace. Sounds overlap, movement feels constant, time seems to accelerate, the contrast is sharp. In the depths, nothing rushes. At the surface, everything does, yet the water remains unchanged. It continues to circulate, to store heat, to carry nutrients, to cradle life that will never be seen. It does this whether or not anyone is thinking about it, whether or not it is being studied, whether or not it is remembered, and that is perhaps the most grounding realization of all. The most isolated waters on Earth do not exist for us. They do not respond to our curiosity or our absence. They are not waiting to be discovered or understood. They simply are. Their processes unfold on timescales that make human concerns feel fleeting. But that does not make them irrelevant. In fact, it makes them foundational. They shape climate. They stabilize ecosystems. They store the past and influence the future. They provide context for understanding life itself, not as something dramatic or exceptional, but as something persistent and adaptive. When we drift back to the surface, we carry that understanding with us, even if only faintly. It shows up as a pause before reacting, a moment of perspective when things feel overwhelming, a quiet awareness that much of what matters happens slowly, beneath the level of attention. It also reshapes the way we think about isolation. What once felt empty now feels full. What once seemed lonely now feels self-contained. The idea of being alone shifts from something to fear into something to consider more carefully. Isolation, in nature, is not abandonment. It is a condition that shapes, preserves, and sometimes protects. The deep ocean does not suffer from its isolation. It thrives within it. And perhaps there is something to learn from that. We live in a world that values visibility, speed, and constant engagement. Yet some of the most stable systems on Earth operate in near invisibility. They change slowly. They resist disruption. They endure. The water does not seek attention. It does not demand understanding. It simply continues, carrying its histories, its chemistry, its life forward through time. As we return to the surface to lighten noise and movement, there is a quiet invitation in that realization. An invitation to slow down, to recognize that not everything needs to be immediate or loud to be meaningful. The deep reminds us that endurance is a form of strength, that silence can be active, that stillness can hold complexity beyond measure, and perhaps most importantly, it reminds us that we are part of a much larger system, one that existed long before us and will continue long after. A system that does not revolve around human presence, yet includes us nonetheless. There is comfort in that, if we allow it, because it means that even when we are not watching, even when we're not listening, the world continues to function with quiet precision. Life persists, Water moves, time accumulates, and somewhere, far below the surface, in places untouched by light or sound, the planet continues its slow, steady work, not waiting, not watching, simply being. And as we surface from these thoughts, carrying with us the stillness of those depths, we return to the world a little differently than we entered it, not with answers, but with perspective.